To introduce our project, our group decided to build the upright robot. The design goal of the project was to construct a self-balancing robot using a feedback control system. For this system, we used a PD, or proportional derivative controller, combined with a gyroscope, accelerometer, DC motor driver, and a power source. The problem we are trying to mitigate is that the mass of the robot creates a torque that tilts the robot. The torque created from the mass is counteracted by the acceleration of the wheels, which creates a force on the center of mass pivot.
As the robot begins to tilt, the sensors tell the Arduino the angle, angular velocity, and the direction in which the robot is falling. The Arduino uses pulse width modulation to send an output voltage to the wheels depending on the values given by the sensor. The greater the angle of tilt, the greater the voltage output, and thus the faster the wheels turn.
The control principles are to stabilize the system and minimize the steady-state error. Our initial system is unstable. Proof can be seen when the open-loop poles of the systems are analyzed and at least one lands on the right half plane of the S domain. To stabilize the system, we introduced a PD controller, which is able to stabilize the system by influencing the first and zeroth order term. The proportional gain constant is to accelerate the response, leading the system to a desired state sooner. The oscillation created by this is counteracted by the derivative gain, which decreases the overshoot. The optimized controller gain will create a double pole on the real axis, and the exact gain factors can be done by testing and tuning. As steady state reaches zero, the system approaches stability.
The frame of the robot was first designed using Inventor and was then fabricated out of wood. We decided upon 3 shelves to house the components of our design. On the bottom shelf, we have the L298 motor driver and the 2 9-volt batteries. One battery powers the motor driver and the other powers the Arduino Uno.
The Arduino is attached to the second shelf, and a hole was cut out into the side so that we could connect the Arduino to USB and upload the code. Finally, on the top shelf, we appropriately oriented the L3GD 20H gyroscope, along with the ADXL 335 accelerometer. Attached to the sides of the robot, on the base, are 2 gearbox DC motors and 2 wheels.
The microcontroller we chose was an Arduino Uno. The Arduino uses pulse width modulation to output an analog-like signal using a digital signal. We can then use the Arduino software to interface with the controller and tell it exactly what to output at certain pins. The controller also has a variety of input pins to read signals received from the sensors. More specifically, we read outputs from the gyroscope and the accelerometer to decide which direction and how quickly we want the motors to move. An H-bridge PCB is then used to simplify the communication between the Arduino and the wheels.
Our robot did not perform up to our expectations due to hardware limitations. Due to static friction in the wheels, we implemented a compensator through our code to turn up the voltage at small angles and initiate the wheels. However, the robot was not heavy enough to create friction between the wheels and the ground, which caused a slipping action. In addition, the wheels did not have enough traction, causing more slip. Finally, the DC motors simply did not generate enough torque to appropriately correct the tilt of the robot. A future design of the robot would include higher quality wheels and motors.